Hello students, in this session we will do the chapter structure of atoms. See, we will be able to separate this chapter into two sections. Got it? In the first section, you will have the experiment to measure the charge of the electron, okay? Then you will have Bohr atomic model, Rutherford atom model, Thomson atom model. Then you will have like de Broglie wavelength, wave nature of the particle, wave nature of the electromagnetic waves, particle nature of the electromagnetic waves. So you will have all those different things that will be in the first section of this chapter. Got it? I'll not touch that section. Okay, so that section will not be taught in the chemistry class because we will do that one exhaustively along with the derivation everything in the physics 12th standard, right? So that will be in the second volume of the 12th standard book, where you will have this chapter which is called as dual nature of radiation and matter, where we will do exhaustively the particle nature of the light waves. Same way you do have like ray optics, wave optics, where we will do the wave nature of the electromagnetic waves. Same way we will learn exhaustively about the atoms in the chapter like atoms. Got it? So Rutherford atom model, Bohr atomic model, and then the line spectra, emission spectra, everything will be learned in the physics. Purposefully I'll not touch that section because those topics will be clearly taught in the 12th grade in the physics part. Okay, so if you look at that theory part in your textbook, that will be like an overall understanding that they would have given you for this particular chapter. I'm just leaving it purposefully so that we can learn exhaustively in the 12th grade of the physics. Got it? So I'll just only teach the second part of this chapter, structure of atom. In the second part of this chapter, we will have the quantum numbers. So you have got like 4 different quantum numbers. So the second part will mainly be related to quantum mechanics. So quantum mechanics is beyond the scope as if now, right? So we do not want to know about the quantum mechanics, the understanding behind it. Only stuff that we need is how should we actually interpret those formulas. So I'll give you a certain formula, you'll have to memorize it, and how should I actually interpret that formula to designate the electrons and things of that sort, right? So here we will learn quantum numbers. So you have got like 4 different quantum numbers: principal, azimuthal, magnetic, spin, quantum number. You might have learned these terms already in your lower grades, right? So we'll just add extra step to it, and then I'll tell you what is the shape of p orbital, p, and then is orbital. Everything will be learnt based on the quantum numbers. So I'll not teach you the proof or the basic behind the quantum mechanics because that is beyond the scope, right? That's not needed. Got it? Then you will have, then we will see like Aufbau principle, Polish exclusion principle, and and then you have got like one more principle into it. So we will learn like some principles that will be related to quantum numbers. Got it? So that part will be done. Fine. So finally you will have like Heisenberg uncertainty principle, which will also be dealt. Only the principle that I'll tell you. Same way, I'll give you one more formula which you need to memorize it, right? So you do not want to worry about the background, the theoretical background behind it. Only stuff that you need to know is I'll give you certain formulas and I'll explain you that formula. That explanation in and itself is enough, right? Got it? So to complete this second part of this particular chapter, structure of atom, first part, I'll not do it, right? I've told you. To complete this chapter, I just need around like 2 sessions. In this first session, we will do 4 different quantum numbers. Same way, I'll just do the Aufbau principle. Rest all other stuff will be done in the next session, where we will see how does the structure of atom is dealt, what is meant by node, and all those other understanding will be done in the next session, right? So I just need like 2 sessions to complete this chapter. So this chapter consists of 2 different parts. First part, I'll just leave it. Only one, I'll just cover the theory part of the second stuff, okay? Right? You shouldn't have any confusion in this one. So obviously I'm not going to teach you the entire chapter, right? The first part of this chapter will be done in the physics 12th standard. Got it? Yeah, that will be enough. Once you are thorough with that theory in the physics, you will obviously be able to solve the sums that they are asking you in this chapter with respect to the first part. Okay. Same way, the PVQ that I will do will be from only from the second part, right? So you got around like 35 questions that will come from this chapter, right? That has come from this chapter till 2000. Fine. Now we can see the quantum numbers. Here you have got, as usual, 4 different quantum numbers, which is principal quantum numbers, azimuthal quantum number, magnetic, and then the spin quantum number. You might have learned these terms already in your lower grades. I'll just give you like one more extra understanding to all these quantum numbers that we have seen, right? First, let me explain you the significance of knowing this quantum number. So if you only know the quantum number of particular electron, I'll be able to locate that electron around the nucleus, right? So if I have to designate particular electron around the nucleus, then I need to know the quantum number of that electron. Only if I know the quantum number, I'll be able to designate where that particular electron is present around the nucleus, right? So to get that one, to get the position, I just need to know these quantum numbers, right? So every electron around the atom will have some set of principal, azimuthal, magnetic, and spin quantum number to it, right? So these number helps to designate the position of the electron around the nucleus. Got it? Fine. So first, let me tell you the principal quantum number. So this is from the primitive basic understanding. Got it? In the physics, I'll just do the Bohr atomic model where I'll use this principal quantum number. Fine. So this is from the basic understanding. So principal quantum number helps us designate the energy level or the shell. So it helps us to determine the energy level, in which energy level my electron is present. To get that one, I just need to know the principal quantum number of that electron. Got it? So this is represented by, so the designation that I'm going to give, or the letter that I'm going to use to represent this one, will be KLMN. Fine. So the letters that I'm going to use is K, L, M, N. Fine. So when they tell you the principal quantum number, something that has to strike you is they're telling us the energy level of the shell. So this is the first reference that I'm giving to that electron. Got it? Now, this is generally represented by the alphabets K, L, M, N. Then, if I have to get the number, if I have to designate it with number, I'll just use the number 1, 2, 3, 4, right? So K will match with the number 1. Same way, L will match with the number 2, 3, 4, and then it just goes on. So this is the number that I'm going to use. So here I'm just using the natural number, right? So yeah, this is not the whole number. I'm using over here the natural number. Got it? Then I'll give you the formula straight away. So this is one of the formula that you need to memorize. So to get the number of electron in particular energy level or shell, the formula that I need is 2n square. I'll give you this formula straight away. You do not want to worry about the background behind it. Got it? So with what logic I got into this formula is not needed. Only thing that is needed is the formula, which is 2n square. 2n square. Now I know the formula. By using this formula, I will have to figure out how many electrons will be there in the K shell. How many will be there in the L shell. That is something that I need to get. So K shell actually matches with the natural number 1. Same way L will match with 2, 3, and 4, right? So accordingly it goes. The formula over here, which we need, is 2n square. For the K shell, n will be equal to 1, obviously. So if n was equal to 1, then if I substitute 1 in this above equation, 2n square, that will be like 2, 1 square, which will give me 2 electrons. That should be obvious. Therefore, in n equals 1, I have 2 electrons into it. Got it? Then let me substitute n equals 2 in this equation. If I do substitute n equals 2, you'll have like 2 square, that will give you 4. 4 into 2 will be 8. Got it? So in L shell, you have got 8 electrons. Right? So 8 electrons, if it is stable and all the shell, I mean, all the electrons are there in this L shell, maximum number of electrons I'll be able to put it in the L shell will be equal to 8 electrons. So 8 electrons will have the designation L to it, right? So this is the first reference that I'm giving to particular set of electrons. In the N shell, you have got 2 electrons. Same, I mean, in the K shell, you have got like 2 electrons. In the L, you have got like 8 electrons. Same way, if it was like 3, just use the same formula. 3 square will be like 9, right? So 3 square is 9. 9 into 2 will give you 18 electrons that will be there in the M shell. So it just proportionally increases in this fashion. That will be 2n square. The idea and logic should be clear. Now just let me put the electrons in the shell. In the center, you have got this positive nucleus. obviously the nucleus will be positive because it contains neutron and then the proton. That logic should be clear. That's going to be positive. So depending on the number of protons, you will have the same number of electrons if the atom is neutral. For example, if it was helium, you'll have like 2 protons into it. Same way, you'll have like 2 electrons in it, right? So those 2 electrons will be in the K shell, because first it will fill the K shell, then it will move to L shell. That's possible. So here, let me put the 2 electrons. Got it? So you'll have like 2 electrons in the K shell. So the first shell designation will be K. I can call this one shell, or I can call this one energy level. Both those terms represents the same understanding. That should be clear. Then you have got L shell. In the L shell, I'll be able to put like 8 electrons into it. So you will have like 8 electrons, 1, 2, 3, 3, 4, 5, 6, 7, 8. Got it? So this is what is meant by principal quantum number that you need to know, right? For whatever natural number that they give you, if you have to get the number of electrons in that particular shell, what I'll have to do is I'll just have to use this formula, which is like 2n squared. So you just need to memorize this formula. That should be known, right? So after 8, you will have 1832, and then it just goes on in this fashion, right? This logic should be clear. Then we will see azimuthal quantum number, the next quantum number, which will be azimuthal quantum number. Next one is azimuthal quantum number. So the letter that I use to designate azimuthal quantum number will be L, right? So the small l will represent azimuthal quantum number. This azimuthal quantum number will help us determining the shape of the subshell. So you have got a shell. Inside the shell, you will have subshell. To determine the shape of the subshell, I'll use this azimuthal quantum number, right? Yeah, you'll get question from this statement based question from this logic. So here azimuthal quantum number helps us determining the shape of subshell. So inside the shell you will have subshell. So shell or energy level will be matched with the principal quantum number. Shape of the subshell will be matched with azimuthal quantum number, right? For azimuthal quantum number, I'll use whole numbers. Got it? So as I'm going to use whole numbers, it will be from 0, 1, 2, 3, 4, and then it goes on. So 4 will be the maximum that is needed. The corresponding alphabet that I'll use to designate will be S, P, D, and F. Okay, so S, P, D, F, G, and it goes on. Got it? So here you'll have for the 0, it will be S, and then for 1, you'll have like P, for 2, D, 3, F, for 4, you have got like G. So this is how I'll match this number with the alphabet. But in the case of principal quantum number, I matched it with K, L, M, N. Here, I'll match it in this fashion, S, P, D, F, G. You'll have to memorize this one as such. You got no other option, right? So F will be the maximum subshell that will be needed. After F, you will have like G into it, right? Next, I'll get the possibility of number of subshell in the shell, right? So to get that one, I know if it is like 1, the possible if the principal quantum number was equal to 1, this is the shell. Okay, if the principal quantum number was equal to 1, you will have one subshell into it, that will be S. Okay, so only one is possible. Therefore in this situation only one is possible. If only one is possible, obviously this starts from the whole number, therefore it is 0, and this subshell will be S. Then when you have got the principal quantum number to be 2, when n equals 2, the possibility of subshell will be obviously 2. So you will have like 2 subshells with the principal quantum number that is equal to 2, right? As if now it might be something new, but then we'll use like off-bow principle and everything to plug in different electrons into different subshells based on the increasing level of energy. Okay, that will be dealt in the later part of this session or in the next session. Got it? So with the case of shell, if n was equal to 1, then the possibility is you will have like one subshell into it. Then if you have like 2 shell, if n was equal to 2, principal quantum number was equal to 2, then the number of subshell possible is like 2. Okay, so Here one S shell will be there. Same way, one P subshell will be there, which will be like 0 for the S and then 1 for P. This is possible. When N will be equal to 3, obviously 3 subshells are possible. So S, 1 will be P, and then for 2 you will have like D. Got it? While notating this azimuthal quantum number with the alphabets, I'll use the small letters S, P, D, F, G. But in the case of principal quantum number, I'll use the capital letters K, L, M, N. Got it? This one should be clear, right? So while just writing electronic configuration, which we will do in the next session, I'll use numbers for the principal quantum number. For the subshell, I'll use the alphabets S, P, T, F. You'll get used to this notation. Got it? Then we have got the magnetic quantum number, right? The next one is magnetic quantum number. Here, the magnetic quantum number helps us determining the orbitals. The orientation and the number of orbitals will be determined using the magnetic quantum number. So inside the subshell, so each subshell will have orbitals into it, right? So this one, magnetic quantum number, will help us determining the number of orbitals and then the orientation, in which position that is oriented. Fine, so we'll see the diagram. So in the case of S subshell, the orbital will be spherical shaped. The subshell orbitals will be spherical shaped. In the case of P, it will be like dumbbell shaped. We will see all those stuff. As if now, what you need to know is magnetic quantum number helps us determining the orientation and the same way the number of orbitals into the subshell. So you have got a shell. Inside the shell, you have got subshells. Same way with the case of subshell, you have got orbitals into the subshell. Okay. So this one helps us determining orientation and orientation and number of orbitals in a subshell and number of orbitals in a subshell. Got it? Fine. So I'll use like integer to find out the orbitals. Got it? So here the subshell will be S, P, D, and F as usual. So F is the maximum extent that is needed. G wouldn't be needed. Okay. So you have got like only 120, 130 elements. So for that much particular amount of elements, this F subshell in itself is good enough. Got it? So that's the maximum extent that we will go. Fine. Here for the S subshell, you have got one orbital into it. I have told you, right? We will designate using integers. So for the first one, the number that I'm going to give is actually 0. That will be for the first one. Then for the P subshell, you will have 0 plus 1 negative 1. Then for the D, you will have 0 plus 1 negative 1 plus 2 negative 2, right, as usual. Then for the F subshell, you will have 0 plus 1 plus 2 and then plus 3. Okay. Then here negative 1 negative 2 negative 3. Got it? So this is how you will have orbitals into the respective subshells S, P, T, and F. Fine. So from this proportionate increase to determine the number of orbitals in a subshell, the formula that is needed is actually M, because to designate the magnetic quantum number, I'll use the letter small m. Fine. So M will be equal to 2 L plus 1, right? If I substitute L equals 0, L equals 0, subshell is designated by L, isn't it? So if L was equal to 0, that will be 1. So that will give me only one orbital in the S subshell. In the case of P subshell, you have got like 3 orbitals, because if I substitute 1, it will give me 2 plus 1, that will be 3. Same way for the D, it will be like 5. Got it? And then for the F, it will be 7. So this is something that you need to know regarding the magnetic quantum number. Then we'll see the final one, which will be spin quantum number. Spin quantum number help us determining the direction of spin of the electron in an orbital, right? So in each orbital, you will have like 2 electrons into it. So this spin quantum number will help us determining in which direction the electron is spinning. If one is like plus in the positive direction, then the other one will be in the negative, in the other way around, right? So do not worry about the logic behind it. Just know this one as such. That's it. Got it? So here spin quantum number will help us determining in which direction you are having the spin of the electron, because in each orbital 2 electron is possible to fill into it, right? So will be 2 electrons in an orbital. So this one helps us determining the direction of the spin. Therefore, in each orbital there will be 2 electrons. There will be 2 electrons in an orbital. Got it? Yeah. If it was S subshell, yeah, if it was like S subshell, obviously only one orbital is possible, isn't it? So with the case of S subshell, you have got like one orbital, and in that orbital, the possibility is you can have like two different electrons. One will, if one has like positive spin, then the other one will have the negative spin. Got it? So here, if one was positive, if one has positive spin, and the other one will have negative spin, minus half. Fine. Same way with the case of p subshell, you have got like 3 orbitals into it. Therefore, you will have like 6 electrons in it. If it is completely occupied, then you'll have 6 electrons into it. Got it? So here, with the help of quantum number, what I'll be able to designate all the 4 quantum numbers for a particular electron, which will help us in locating the electron around the nucleus, right? So to get the location of the electron around the nucleus, I'll use this 4 different quantum numbers, which is principal quantum number, azimuthal quantum number, spin quantum number, and then the magnetic quantum number, right? You should be clear with these 4 different quantum numbers and the basic understanding behind it, which is completely enough for solving sums in chemistry. Then you have got shapes of atomic orbitals. So next, I'll have to find the shapes of atomic orbitals. I've told you already, azimuthal quantum number will help us in determining the shape of this atomic orbital. So just know the shape, which is enough. You got it? A subshell. So here, S subshell will have like spherical shape. Okay, so here you just have like only one spherical shape in it. This will have only one orbital into it. Therefore, 2 electrons is possible to fill in this S subshell. Got it? Then you have got like P subshell. So this is like S orbital, right? Then because in with the case of S orbital, you just have only one subshell into it. Therefore, here you have got one subshell. Same way you have like one orbital into it, right? With the case of P subshell, this is like dumbbell shaped. Okay, so P subshell has like 3 different orbitals into it. Therefore, p orbital will be dumbbell shaped. By the way, you will have like 3 different p orbital. So one of the dumbbell will be along the x-axis. Got it? So this is like a 3-dimensional representation they've drawn over here. So you've got like x, y, and then the z. Got it? So if that's the case, let me take it this way. With the case of n equal to, which means when principal quantum number was equal to 2, the possibility is you can have 2 different subshell into it, which is like 2s and then the 2p, right? For the s, the possibility is spherical shaped, but in the case of 2p, you can have like 3 different orbitals into it, right? So p subshell will have 3 orbitals into it. Therefore, those 3 orbitals will be in dumbbell shaped. One will be along the x-axis, so that is like px, p along the x, p orbital along the x. Same way, p orbital along the y. So this one will be like py. Then you have got p orbital along the z, that will be like pz, which will be directed along the z axis, right? So now I hope this diagram clearly shows you the shape of s orbital. Same way it shows you the shape of p orbital. Okay, so in this p subshell you have got like 3 orbitals, right? So this will tell you the shape of the p orbital, which is like px, py, and then the pz, right? This should be clear. Then one more shape is left, which will be for the d orbital, right? So with the case of d orbital, it will be double dumbbell shaped. Okay, so that's how it is going to be. I know for d subshell, the possibility is 5 different orbitals into it, right? So I'll have to generate 5 different shapes by using double dumbbell shaped. I'll get like 4 different lobes. Okay, so 4 different possibility is I'll be able to get this four different possibility. But the other one possibility will be like a kind of dumbbell and then the donut shaped, right? Let me tell you all those stuff. So first, it's like double dumbbell shape with the case of d orbital. So the first orbital will be dxy, which means this four lobes will be in the plane of x and then the y. Okay, so it will not be along the z plane, so it will be in the plane of this x and then the y. Got it? So you'll have like four lobes into it. So this one will be dxy, right? That should be clear. Then the next one, obviously you'll have to make multiple combination from it. The one will be xy, then the next one obviously has to be yz, then the next one has to be between xz, right? So that's how, right? X, Y, Z, that is possible. So the first combination is XY, then the next combination will be YZ, then the other one, the third one will be XZ, right? So here for the YZ combination, you will have like same way, double dumbbell shape. This will be in this YZ plane. Got it? So this one was a kind of flat paper. So this one was in the xy plane. So this one is actually vertical to it. So let me give you an example. If the first one was like flat, then the next one will be perpendicular to it. It's a three-dimensional understanding that you have to generate. Obviously, it should be easy while looking at it. Got it? So here the first one is like the xy plane. Then the next four lobe will be along the yz plane, yz plane. Okay, and then the next one is actually in the plane of xz. Fine. So if one was in this fashion, then the other one will be perpendicular to it. Then the next one will be perpendicular to it, right? So the possibility is like three different plane in three dimensional, isn't it? So in all those three different planes, you will have double dumbbell shaped d orbital, right? You should be clear of this one. So the first is like dxy, then the next possibility is dyz, then the next one is dxz, right? Fine. So finally, I'm just going to draw one more possibility into it, which is like dx square minus y square. So this dx square minus y square will be in this xy plane, but along the axis. Here it wasn't along the axis, it was actually between those two axes, right? At an angle of 45-degree diagonally. But here it is along the axis, right? So it is along the axis of x and then the y plane. So this is like dx square minus y square, right? So don't worry about this notation, just memorize it as such. That will be enough to solve sums. Dx square minus y square. So one will be along the x-axis and the other one will be along the y-axis, which is like dx square minus y square. Finally, you have got dz square. So this dz square, the name clearly suggests the one of the dumbbells should be along the z-axis, right? So one will be along the z-axis and the other one is actually donut shaped. So here this is the only odd shape for this double dumbbell shape with respect to the d shell, d orbital. So that one will be dz square. So one is like dumbbell and then the donut shape. So if they're asking you which one is odd, then actually dz square is odd, right? So if they tell you like dz square, then it is for sure one is like dumbbell and the other one is donut, right? This is what you need to know regarding the shapes of SPD. Don't worry about the F, that's not needed. So you should know only these three shapes, which is like S. For S, it is spherical shape. With the case of p orbital, it is dumbbell shape. With the case of d orbital, it is double dumbbell shaped. You have got like two dumbbells into it. Same way, only one is like odd in it, which is dumbbell and then the donut shape. That will be for the dz square, right? So you should be clear with this notation that I've written over here. You should just by heart it as such. Right, simple, easy way, just a basic understanding. That's it, finished. Fine. So next, I'm just going to fill the electrons in all these shells and I'll tell you in which pattern you have to fill it, right? For filling electrons around the nucleus, two different scenarios are there. The first one is monoelectronic atoms, which means you just have only one electron in that atom, right? If that was the case, then it will be in simpler fashion. Same way, in majority of the situation, it's going to be multi-electronic. Okay, so if that's going to be the condition, then for the multi-electronic atom, we will use like Aufbau principle. I'll tell you what is meant by Aufbau principle, right? With the case of monoelectronic atoms, you don't have the interaction between electrons and then the electron, right? So in that situation, it will be simple. Got it? So I will not use Aufbau principle with the case of monoelectronic atom. The way it fills is, first you will have 1s, which means principal quantum number was like 1. Obviously, in the 1, you will have only one subshell, which is 1s, right? So that will be 1s. Then the next one will be like 2s. With the case of principal quantum number 2, you will have two different subshell into it, which will be like 2s and then the 2p. So you will have 2s and then the 2p. As this is monoelectronic, there wouldn't be any interaction between the electron. So in this situation, 2s and 2p will have same energy level. Got it? So 2s and then the 2p will have same energy level. So this is how it is going to increase. So when we are dealing with the monoelectronic atoms, we will learn this Bohr atomic model. While doing Bohr atomic model, we will only be worried about this principal quantum number. We will not consider this azimuthal quantum number because that thing is insignificant, because 2s and 2p just has the same energy into it, right? So here the first one is 1s, and then you have like 2s and then the 2p. Obviously these two 2s and 2p will be merged, which means it will have the same energy level into it. So 2s will be equal to 2p. Then obviously this one will be less, which will this one will be less when compared to 3s. It will also be equal to 3p. This one will also be equal to 3d, right? So here this is how the energy level is going to increase. The electron in the 1s will have low energy. Got it? Same way, the electron in the 3s or the electron in the third shell will have more energy into it when compared to this one. So here it has low energy and here it has high energy. The possibility of electron over here is only 1. So when it is at n equal 1, it will have the low energy. Same way, if it gets excited, it goes to the shell 3. So when it is in that position, it will have high energy into it. Okay, so when it has low energy, which means it is stable. Fine, if I have to activate it, and then if that has to be the condition, then I'll have to give energy into it, right? So when it gains energy, that electron, when it gains energy, it jumps to the higher energy level, then obviously it will be unstable, right? So the lower the energy, more it will be stable, which means that electron is very close to the nucleus and that atom is stable. Higher the energy, that electron got excited, as I have given energy to that atom, therefore that atom will be unstable because the electron is excited to the higher energy level, right? So low energy actually means that is stable. It's like a comparison that you do between the earth and then the sun. Okay, the sun has more energy into it. It is just burning. It is just giving out lots of energy, right? So it is high energy, which means it is unstable. With the case of the air, it is stable, okay, because it has low energy into it, right? Fine. So it's a kind of same perception. So low energy means it is more stable, but if the energy is more, then it is like high energy, right? Just get a comparison between the sun and the earth. The sun is unstable, it is completely burning, it is releasing photons, tons of photons. Same way with the case of earth, it is much more stable when compared to the sun, right? So that's the intuition. So low energy means it is more stable, high energy means it is less stable or unstable comparatively. Okay, so in the case of low energy, it is stable, the atom is stable. With the case of high energy, if the electron got excited, it has absorbed the energy, therefore this is unstable or less stable, whatever it is. Fine. So here I didn't use of Bohr principle. So to get this one, for this one, no of Bohr principle is needed. Yeah, no of Bohr principle is needed. Okay, yeah, it should be clear. Then I have drawn one more diagram to it. Here the first one is like 1s. Yes, this is the lowest energy level, and then you have got 2s, 2p. These two stuff has the same energy into it. Then you have got 3s, 3p, 3d. This one will also has the same energy into it. Fine. So the example for this monoelectronic atom will be obviously hydrogen. That's the first one. Next one is helium. Helium has two electron into it. It is stable. It comes into noble gas. So it is stable. If I remove one electron from it, it is hard to remove that one electron. Anyway, if I remove one electron from it, it will form helium plus. Okay, so this helium plus will also have only one electron into it. Therefore, it becomes monoelectronic atom or species. Then Then obviously Li2 plus. So Li2 plus also comes into this monoelectronic atom. Fine. So these three is the only example for the monoelectronic atom. Then you have got multi-electronic atom, right? So to get the multi-electronic atom, I just need to use this off-Bohr principle. Got it? So to get this off-Bohr principle, as I've already told you, do not want to worry about the basic, background understanding for this off-Bohr principle. Just I have a notation. We have a notation to notate this energy level, right? So to do that notation, this is how I just need to write the energy level same way along with the subshell. So for the first one, you have got 1s. Then for the second subshell, then for the second shell, you have got 2s 2p, then 3s 3p 3d, 4s 4p 4d, 4f, then 5s 5p 5d 5f. It goes on 5g, that is possible, but we don't have atom to fill for that one. Then 6s 6p 60 70, and it just goes on, right? So this is enough to get the Aufbau principle for multi-electronic atom. For K, so this one will obviously be for the K shell, isn't it? So this one is K shell, and then it has 2 electrons into it. Then you have got like 2s 2p. So this will be for the L shell. You have got 8 electrons into it, because for the P subshell, or for the P subshell, you have got 6 electrons. So 6 plus 2 will give you 8 electrons. And then for the M, you will have 18. So 2, 6 will give you 8, 8. And then for the D, you will have 10 electrons is possible to fill over there. So together it will give you 18 electrons. Okay, right? Yes. And then it goes on. The formula pattern will be 2n square. It should be clear. Now, let me tell you in what fashion I'll have to arrange it based on the increasing order of energy level. Got it? So you have got some yeah, a kind of pattern. Let me draw that pattern over here. First, I'll just fill 1, then I'll go to 2s, right? So remember this pattern as such itself. So 1 and then 2s. Then after 2s, you will have like 2p. Got it? Then after 2p, you'll get like 3s. So this one, up to this one, it will just go in a correct fashion. Then after 3s, you'll have like 3p. Then you will not have 3d. Then you'll have like 4s into it. Then after 4s, you'll have 3d. Then you will have 4p 5s. Then after 5s, you will have, then after 5s, you will have 4d. After 4d, 5p 6s. Then after 6s, you will have 4f 5d 6p 7s, and then it goes on. So this is the pattern that you need to know, right? Now just let me write the increasing order of energy level for multi-electronic atom using Aufbau principle. Now I have just drawn that pattern. Let me write it in the increasing order of energy level. With the case of 1s, that will be the lowest energy level. So the energy level keeps on increasing. For the low energy level, it is more stable. The electron in that energy level will be more stable when compared to the electron which is in the higher energy level. Got it? With the case of monoelectronic atom, only 1 electron was possible, but that's not the situation here. It is more than one. Okay, so this is multi-electronic. The first one is 1s, then you will have, which is less than 2s, 2p, fine, same way 1. Just by looking at this diagram, I'll be able to write this increasing order of energy level, 1s, 2s, 2p, then you will have 3s, and then you will have 3p, then after this 3p, you will have 4s into it, then after this 4s, you will have 3d, okay? Yeah, then you have got 4p, and then 5s, 4d, 5p, 6s. Okay, it just keeps on going, whatever it is, 4f, and then 5d, right? You can just keep on writing this one, right? So this is the increasing order of energy level using Aufbau principle, right? You should be clear with all the concepts that I have taught you. In the next session, we will do the rest all other chapter, which will be Pauli's exclusion principle. It's just a one statement that you need to know, hence rule. And then we will use this Aufbau principle for filling of electrons with the case of scandium, titanium, vanadium, we'll do that one, right? So how to use this Aufbau principle, all those stuff will be done in the next session. Same way, we will see like one more extra concept into it, which is like the nodes. With respect to this p orbital, s orbital that we have studied, we will learn something called a new concept, which will be like a node, right? So all those stuff will be done in the next session. So in this session, what you have seen is like 4 different quantum numbers: principal, azimuthal, spin, magnetic quantum numbers. So these quantum numbers helps us designating the position of the electron around the nucleus. Okay. Same way, after that we have seen this arrangement of energy level for the monoelectronic atom. It is simple. You just have to consider only the principal quantum number. With the case of multi-electronic atom, you'll have to use the Aufbau principle. I've told you that one also, right? You shouldn't have any doubt in all the concepts that we have seen. It has to be clear. Fine. With this, the video gets completed.